When you switch a circuit on, its behavior is not immediately stable. It first goes through a changing phase before eventually settling into a stable condition. In this lesson, we will clearly distinguish transient response from steady-state behavior and understand how both define real circuit operation. In circuit theory, the response of a system is divided into two main parts: transient response and steady-state response. The transient response describes the behavior of the circuit immediately after a change in input, when voltages and currents are still adjusting over time. The steady-state response describes the condition where the circuit has stabilized and no longer changes with time in a predictable way. Transient behavior occurs because energy storage elements such as capacitors and inductors prevent instantaneous changes. During this phase, the system is still reacting to past conditions and gradually moving toward equilibrium. This is why voltages and currents evolve over time instead of jumping instantly to their final values. Once all transient effects have decayed, the circuit reaches steady state. In this condition, the system behaves in a stable and repeatable manner, often driven directly by the input signal without influence from initial conditions. The transient component is the part of the circuit response that depends on initial energy stored in capacitors and inductors. It represents how the system transitions from one state to another after a disturbance such as switching, signal application, or load change. This component typically decays over time due to energy dissipation in resistive elements. As energy is lost as heat, the magnitude of the transient response decreases until it eventually becomes negligible. The speed of this decay is determined by time constants in RC, RL, and RLC circuits. Mathematically, transient response often follows exponential functions, which reflect how energy redistribution occurs in physical systems. This makes transient analysis essential for predicting how long a circuit takes to stabilize after a change. Steady-state behavior describes the long-term response of a circuit after all transient effects have disappeared. In this condition, the circuit operates in a stable pattern determined only by the input signal and circuit structure, not by initial energy conditions. In DC circuits, steady state means constant voltage and current values. Capacitors behave like open circuits, and inductors behave like short circuits in ideal steady-state DC conditions. In AC circuits, steady state means sinusoidal signals with constant amplitude and frequency after transient effects have decayed. This distinction is important because steady-state analysis is much simpler than transient analysis, allowing engineers to use simplified models for long-term circuit behavior. In engineering practice, separating transient and steady-state behavior is essential for analyzing and designing real systems. Transient analysis is used when studying switching events, startup behavior, and signal changes, while steady-state analysis is used for normal operating conditions. Power systems rely heavily on transient analysis to ensure safe switching operations and prevent unwanted voltage spikes. Meanwhile, steady-state analysis is used to design circuits that operate reliably under normal conditions. Understanding both behaviors allows engineers to design systems that are stable, predictable, and efficient across all operating conditions. In RF engineering, steady-state analysis is commonly used to study sinusoidal signals in frequency domain, where systems are assumed to operate after all transient effects have settled. This simplifies analysis of gain, phase, and impedance. However, transient effects still matter in RF systems during switching, modulation, and signal startup. These short-term behaviors can affect spectral purity, introduce distortion, or create unwanted harmonics. Understanding both transient and steady-state behavior is essential for designing RF systems that perform correctly during both signal transitions and continuous operation. In this lesson, we learned the difference between transient and steady-state behavior in electrical circuits. Transient response describes how circuits evolve over time, while steady-state describes long-term, stable operation. In the next lesson, we will begin AC circuit analysis and move into frequency domain circuit behavior. If you found this useful, like the video, subscribe, and follow for the next lesson.